Are you going to record the lecture with Zoom?
Yeah. I will try the first time,
Okay.
and see if it works.
Okay.
If it works, then we may get rid of this,
Okay.
because of the clarity of this. Yeah. All right. Good morning, everyone. I think it's time to start. So first of all, I will, to my knowledge, we got a positive case, COVID positive case in our class. I'll highly recommend everybody to wear a mask in the lecture room. And if you want to go to the office, please wear the mask and keep the safe distance. And if there's any update about that kind of things, I'll update you. But just be careful, just to remind you to be really, really careful. Okay. So in the last lecture, our TM Shibo Li has given the tutorial on PyTorch, which is extremely popular. It's a state-of-art neural network library. So if you want to use neural network for your Kaggle project or your exploratory project, please go ahead and use PyTorch. And in your practice, please use those mature, highly efficient libraries. Don't implement everything from scratch. However, because our class is a fundamental class, right? We need to know every details and what's the fundamental ideas and mechanism of neural networks. Of course, in our homework assignments, you're requested to implement the backpropagation algorithm details. But in practice, again, I highly suggest you to follow the examples given by our TMs and try to debug them and get a sense how to leverage those modern libraries to save your time and avoid many unnecessary debugging steps. Okay, today we're gonna continue with the backpropagation, the key technology underlying the neural network training. So in the previous lectures, oh, by the way, because our admin has still yet been able to fix the resolution of the camera issue. So today I'm gonna try to use Zoom to record the lecture, because I'm gonna do many manual derivation to showcase how the backpropagation works. I don't want, like, for example, tomorrow or next week, you're gonna review the lecture, where you see the recording is still a blur. That's not good. So I try to use Zoom to record everything. But at the same time, our TM still use the camera to record the video. So you can choose. We'll post the two links. You can choose whichever you feel comfortable with that. And if this Zoom trick works, so we're gonna use Zoom record for the remaining classes. Okay. So let me. So in the last lecture, we actually have reviewed the chain rule, right? So we have mentioned that the backpropagation essentially is the leverage of the chain rule. I think everybody is familiar with that, right? So, but what we emphasize is that chain rule, the graphical representation of the chain rule. So basically, we can represent all the. Let me see. Where's the? I'm trying to. Sorry. Let me use this laser point to make it better. Okay, it's much better. So for any variables, from which we want to compute the partial derivatives. So we use vertices or nodes to represent them, right? And their direct functional relationship are represented by edges on the graph. For example, if z is a function of y1 and y2, then we draw a link from y1 to z, right? And we draw a link from y2 to z. This just represents z is a function of y1, z is a function of y2, right? And if further y1 and y2 are functions of x, then we draw a link from x to y1 and from x to y2 respectively, right? On each edge, we can compute the partial derivative of the parent node over the partial derivative of the source node, right? So on this link, this represents z is function of y1, so we can calculate partial z over partial y1, right? This partial z over partial y2, and y1 is function of x on this link, so we got partial y1 over partial x, and this link, partial y2 over partial x. Then, if we want to compute partial z over partial x, of course, you can just recite your chain rules formula to do everything you want, right? But we want to give a more intuitive rule from the graphical view, right? That is, we just look at all the passes starting from x and ending at z, right? And from this graph, we know that there are two passes, right? One pass from here, and the other pass is from here. So when we compute partial z or partial x, we just enumerate every path and then multiply all the partial derivatives along each path and add them together. So in this case, the result will be, okay, for this path, in the left-hand side, right? It is just partial z over partial y1 times partial y1 over partial x. Then plus the result along another path, which is partial z over partial y2 times partial y2 over partial x, right? So we got the result. So this is a graphical illustration. This is very useful when we talk about backpropagation because we need to associate with the architecture of the neural network. Okay. So in a more general sense, suppose z is a function of n variables, right? y1 to yn, and each of those intermediate variables is also a function of x. So we can draw a graph like this, right? So if you want to compute partial z over partial x, or you're gonna enumerate all the n passes from x to z, right? And for each pass, you're gonna multiply the partial derivatives along each pass and then add them together, right? That's the general form of the chain rule, right? So then we use the chain rule to showcase how we calculate partial derivative on a example neural network, right? It's just the two-layer neural network. I'm not gonna repeat how we do the forward pass to compute the output, and then we use the square laws. And we have shown how to compute partial L over this edge weight, right? The weight on the edge connects Z0 in the hidden layer to the output node in the output layer, right?
The YouTube video is not showing any.
It's not showing?
Yeah, I can't see it screen.
Oh, that's weird. I have experimented, it should work. Let me take a look. Oh, so it records the video but doesn't record the screen, right? What?
I got the last 5 seconds.
Last 5 seconds shows the screen. Let me Oh, you mean share the desktop? This desktop? And let me. Oops. When I do this, can I see it in the? Can I see it in the video? But you cannot see the video, right? So let me. I guess it's. I need to. I need to first do the. Oh, you can see it now? Thank you. Okay. Okay, let me know if you found any issue. I appreciate it very much. Okay, let us continue with this. So we know if we want to compute partial L over partial this edge weight, right? Apply the chain rule, L is directly dependent on the output node Y, right? So you're gonna first calculate partial L over partial Y, then times partial Y over partial W0 and O, right? So our output is computed by a simple linear combination of the hidden neurons in the hidden layer, the neurons in the hidden layer, and with those weights. So it's pretty straightforward to compute partial Y over partial W010, right? So, I'm not gonna repeat it. And similarly, you can compute the partial L over partial W110, right? And then we look at how to compute the partial L over partial W22H, which is on the edge connects X2 in the input layer and Z2 in the hidden layer. So it's a little bit more complex because you move the layer, you move one layer below, right? So again, we apply the chain rule because L is directly dependent on the output neuron Y. So we're gonna first compute the partial L over partial Y, then partial Y over partial W22H, right? So, and then this partial Y over partial W22H can further represented because the output Y is directly dependent on all the neurons in the hidden layer, right? Z0, Z1, Z2. So partial Y over partial Z0, partial times partial Z0 over partial W22H plus partial Y over partial Z1 times partial Z1 over partial W22H plus partial Y over partial Z2 times partial Z2 over partial W22H, right? But the key observation is here. Z0 and Z1 actually do not depend on W22H, right? Right. This is I mean, you can just look at the rule of the neural network forward pass. You can see that Z0 is just constant 1. Z1 is computed from the input neuron for sure, but they are based upon another edge weights, right? In other words, W22H stays on the edge, which never connects to Z1 or Z0. So from the structure point of view, actually W22H is not related to Z0 and Z1 as well. So that's why, I mean, the graphical view of the chain rule is also important. I want to emphasize that point. So then we can safely cancel out the first two products in the parentheses, right? So then our results is partial L or partial Y times partial Y over partial Z2, then times partial Z2 over partial W22H, right? So now let us look at how do we compute each of these three terms in the product. So the first one for sure is Y, and one is Y star. Y star is the ground truth. We all know the result. It's pretty straightforward. And the second one is easy as well because the output neuron is a simple linear combination of the Z0, Z1, and Z2, right? It's pretty straightforward to compute the partial Y or partial Z2, right? And the third one, we need to be a little bit careful. Z2 is computed from the input neuron. So because Z2 is in the hidden neuron, is a hidden layer, it's not in the output layer. So that means the value of Z2 is computed by first a linear combination of the input neurons, and then perform an activation function, right? This is our rule, right? So, and then how do we compute the partial Z2 over partial W22H here, right? Again, we use chain rule, right? If we will, the input of this activation function as a whole, input variable, right? We call this as some intermediate variable like S. Then partial Z2 over partial W22H is first to compute the partial derivative with respect to S, right? And then partial S over partial W22H, right? So of course, partial S over partial W22H is straightforward, right? Because it's just a linear with S. It's just linear to S, right? But then the problem is how do you compute partial activation function with respect to the input of this activation function, right? So any questions so far? This is just an application of chain rule, nothing else. Okay. So, of course, this is dependent on how you choose your activation function, right? As we mentioned before, we actually have a lot of choices of the activation function, right? So you can choose the Sigmoid activation function here. You can use ReLU function, right? And you can use 10H, you can use sine function, whatever. And the different activation function will correspond to different partial derivative here, right? And for this continuous activation function, of course, we can take the partial derivative directly. But I want to ask, what if I choose this? This is called ReLU. How do you compute partial sigmoid or partial S? Any thought? Hmm? Yeah, more general, well, I want to say it in more generally, you actually, if this max function actually is discontinuous, they don't have exact gradient, but you can calculate subgradient, right? Just like what we have done for the hinge loss, right? You can replace the exact gradient by the subgradient. That's it. So, but here we want to show how to compute the partial derivative of the Sigmoid activation function, because this is a well-known result. So I want everybody to know that result, and so leverage them in your implementation of the homework. So I'm gonna switch to the iPad. Let's see how to. Oops. So you guys can still see the slides, right, in the video. Okay, great. Let me stop share this. Share this stuff. Sorry, when I wear the mask, it doesn't work, the Face ID. Oops. Oops. Okay. Oh, let me. Let me make it larger. Okay. You still see the pad on the video, right? Okay, great. Thank you. So hopefully this will look the background a little nicer. Okay. So this is the Sigmoid activation function. I'm going to use the red pad. So it's 1 over 1 plus e to the power of minus s. It's knowing that this is just between 0 and 1. Sorry, it's between 0 and 1. So this is very useful because later when we talk about the logistic regression, you see that we're going to use this as our log likelihood as well. So this is very, very common use. So now we want to compute partial sigmoid or partial s, right? So let us just do this mechanically, right? Use whatever we have learned and practiced numerous times in our calculus course, right? So this one is just the definition is 1 to the e to the minus s to the power of minus 1, right? So now you take the partial derivative. Again, apply the chain rule. You're gonna move the power in front of it, and then take the subtract power by 1, right? Will be minus 2, and then you take the partial derivative of this 1 plus e to the minus s, right? So which is simply take partial derivative over here. So it will be e to the power minus s, and then take the partial derivative over negative s, which end up with minus 1, right? And well, you see 2 minus 1 here, so just cancel, right? So you got e to the minus s in the numerator plus over e to the minus s squared, right? Well, if you arrive at this point, you have obtained the result, but here I will give you an even better form. So the key idea is that, okay, because this is just the power of a square of the 1 plus e to the minus s in the denominator, right? So why not we just expand it? So now we can write it as e to the minus s over 1 plus e to the e to the power of minus s times 1 over 1 plus e to the power of minus s, right? This is correct, right? So now, what's this? Yeah, it's Sigmoid itself, right? And what about the left term? Any idea? It is 1 minus sigmoid s. Right? You can just try to do that, right? 1 minus 1 plus e to the minus s. It is exactly this guy, right? So this is a well-known result. So if you take derivative of the sigmoid function, it's just sigmoid times 1 minus sigmoid. And because, you know, signal S is between 0 to 1, you know, 1 minus it is also between 0 to 1. So the derivative is also non-negative, meaning that the signal function is monotonically increasing, right? Because it's a non-negative gradient. So this is a very interesting and useful result. It's not only useful for your neural network work, right? But it's also useful when you will study the logistic regression. Hopefully, this trick will help. Yeah. Okay, so now let us look at the final result, right? So by applying chain rule, we can compute partial Z2 over partial W22H is partial, if we use sigmoid activation as our activation function, right? It's partial sigmoid over partial S times partial S over partial X2, which is simply partial W22H is simply X2, right? And this partial sigmoid over its input is just the sigmoid times 1 minus sigmoid. So we just plug in the result. And finally, we got our results of partial loss with respect to this edge rate partial W to the H. Right? So any questions so far from this computation procedure? It's just okay. Yeah, let me try. Oh, nice. Thank you. Yeah, that's a really good suggestion. Yeah, it was always a headache for me. Yeah, it's too empty in the backend. Yeah, that's much nicer. Okay, nice. Any other suggestion? Yeah, great. Appreciate it. So now let us look at this result again, right? But now from the graphical point of view, right? So let us summarize the computational procedure by leveraging the network structure. Right? So if you want to compute partial L over partial W2 to H, all this L, you can view them as a virtual node, right? Because the output neuron is fed into this loss function, right? The calculus loss function. If you want to compute partial L over any edge rate, right? You're gonna essentially first find out the passes from the target node this edge points to the output neuron, right? So from here, for W2 to H, the edge points to Z2, right? In the hidden neuron, right? And from Z2, we can see that there are only one path going to the output neuron Y, right? They are marked as yellow. So now the computation is just to, multiply all the partial derivatives along this path, right? Of course, at the output neuron, you have to compute the partial loss over partial output neuron Y, right? And then times partial Y over partial Z2, right? This is essentially, if you view this as a parent node, you're actually compute partial parent node over partial child node Z2. And then times partial Z2 over partial W2 to H, right? So you can summarize some computation rule from the graph structure. And it's very easy to find the correspondence because we know that W2 to H, all the neurons only on those passes which connect the target node Z2 to the output neuron Y will be dependent on W2 to H, right? All the other neurons, which are all of these passes, are not dependent on W2 to H. at all. For example, like Z1, it's not on path. And you can see that the computation has never involved W to the H. Okay? And similarly, Z0. Okay? We can see another example, like Z1, right? If you want to compute partial L over partial W01H, how can you do that? Any thought? Yeah. Want to see something? Yeah. Yeah, just look at, okay, the edge where W01H stays on the target node is Z1, right? You just look at all the passes from Z1 to the output neuron Y, right? How many passes do you have? Just one, right? So it's marked here as yellow, right? And so you just compute partial derivatives along the path, right? So at the output neuron, you have to calculate partial loss with respect to partial alpha neuron, and then partial Y or partial Z1, and then partial Z1 or partial W01H, right? So in general, if you want to compute the partial derivative of the loss with respect to any edge weight, right, WMNH, according to our notation, it is on the edge which connects mth node in layer H minus 1, right? And nth node in layer H, right? You need to draw all the paths from node n to Y. Y is the output neuron or the root node, whatever, right? And then you just enumerate all the passes and multiply the derivatives along each path, add them together. It's just what we have done to illustrate the chain rule, right? So now, let us give a formal description about this rule to compute partial derivatives. But this is not backpropagation. It's just to motivate backpropagation. Yeah, we're still doing the appetizer. Okay. So in general, we want to compute each partial L over partial W MNH, right? And here I want to emphasize notation because I don't want anyone to be confused here. It's really important. So for convenience, we generalize notation here. H is the layer number. It's a number. It's an integer, right? And the WMNH is on the edge which connects mth node in layer H minus 1 and nth node in layer H. So the mth node in layer H minus 1 is denoted by Z m H minus 1. So we got superscript, which indices the layer, and the subscript indices the node, right? So you can see that here is the edge which connects mth node in layer H minus 1 and the nth node in layer H, and the edge is in between, and the edge weight is denoted by W, M, and H. Again, H indices the layer of the target node. And of course, just to obey the convention, suppose your output layer T, we're going to index the output neuron by 1, not by 0. So we denote Z1T. Suppose this output layer is layer T, right? So Y is also denoted by Z1T. Okay, so now to compute partial L over partial W, M, and H, we're going to first initialize partial L over partial W, M, and H with 0. Then we find all the passes from Z and H. Remember, Z and H is the target node where the edge points to, right? We're going to find all the passes from Z and H to the output node Y. In our previous simple case, you only find one pass, but in practice, because the large architecture, you might have multiple passes. So don't forget any of those passes. Then for each pass S, we're going to go through each node Z in S. We compute the partial derivative of Z's parent over Z. Right? If the node is the output node Y, then we compute the partial loss over partial Y directly. Right? Otherwise, you just calculate the partial derivative of its parent node over itself. Right? And then you multiply all the partial derivatives along the path S to obtain this results GS. Right? GS is not the gradient, final gradient, it's just part of the gradient. And then you multiply GS with partial Z and H over this edge weight. Don't forget the last step. Right? You get one result, you add it into partial L or partial W, M, and H. You finish one iteration. Right? And of course, you need to enumerate all the passes. You have to go through every passes. You have to calculate partial derivatives along this path, multiply partial Z and H or partial W, M, and H. You add them into them. Finally, you add them all together. You get partial L or partial W, M, and H. That's a kind of like more formal and detailed specification of this computation procedure. Any questions so far? Yeah, let me use one example to illustrate the procedure. Yeah. So suppose from Z and H, right? This is my output neuron, right? So I got 3 passes. I got 3 passes which connect Z and H to the output neuron Y, right? And here, just for convenience, I just ignore the notations we just use. I just use some notations. I denote this is Z0, Z1, and Z2. Right? So now, following this whole procedure, right? Let's see how we compute partial L over partial W, M, and H, right? So first, we need to look at every pass, right? So the first pass is here, right? So it will be, we're gonna add the results along this path, starting from the output neuron, it will be partial L or partial Y, right? And then move to Z0, its parent node is Y, right? So we're gonna compute partial Y over partial Z0. And then you move to Z1, right? Its parent node is Z0. So you're gonna compute partial Z0 over partial Z1. And then you go to Z and H, right? So you compute partial Z1 over partial Z and H. And then you times this. You don't forget last step, which is partial Z and H over partial W, M, and H, right? This is just the result for the first pass, right? We have not finished yet, right? So now we need to look at the second pass. See this one, right? So the computation will be, okay, I'm going to add up partial L over partial Y, okay? And then we move to Z0 again, right? So partial Y over partial, it doesn't look good, right? Let me use another color. Maybe use this, partial Y over partial Z0, right? This is partial L over partial Y. And then you move to the third node in this path, Z and H, right? So the parent node is right now is Z0, so it's partial Z0 over partial Z and H. And then the last step, you need to multiply partial Z and H over partial W and H. This is the second pass, right? And remember, we have a third pass, right? So along this one, right? So I have to compute the third one, right? It's partial L, again, partial L over partial Y, right? And then you move to Z2, right? So it's partial Y over partial Z2, and then partial Z2 over partial ZNH, then times partial ZNH over partial WMNH. So now you finish the computation, right? So any questions so far? It's straightforward, right? But there's a big problem here, right? So you can see that, I mean, this is kind of like a direct application of the chain rule, right? It's intuitive, but it's not very efficient. First, we can see that there are many redundant calculations here. So you can see that first, partial L over partial Y appeared 3 times, right? And also partial Y over partial Z0 appeared twice. And every time you have to compute partial ZNH times over partial WMNH, right? So a lot of like redundant conditions. And also you can imagine the whole procedure. When you go down, right, to the below and below, right? Every time, no matter at what level the edge weight, right? You have to backtrack to the output neuron, right? You have to compute the partial derivatives along the output and until you go down to my current level. So imagine if you have like 100 layers or 200 layers, at each layer, at each weight, you have to backtrack to the like 100 layers top. This is really, really expensive and inefficient, right? So that's why people are motivated to develop a much more efficient algorithm called backpropagation. But I want to, but before I illustrate the idea of backpropagation, I want to use a more complicated examples to show how the backpropagation algorithm is invented, right? Okay, I'm gonna use I'm gonna use a 3-layer neural network. Just forgive my bad drawing. So this is layer 0, this is layer 1, this is layer 2, and layer 3, this is alpha layer, this is Y, right? So again, we assume they are fully connected, right? And they end up this here, right? So this is an input layer, layer 0, input 0, x0, x1, and x2, right? And now I will stick to our notation definition. So this is a z01, z11, and z21. So this is a z02, z12, and z22, right? So now, suppose we want to compute the partial derivative on some specific edge weight here. Right? So it's on the edge which connects x1 in the input neuron and in the input layer and the z11 in the layer 1, right? In the layer 1. So according to our notation, the weight here is denoted by W1, 11, right? It connects the first neuron in layer 0 to the first neuron in layer 1, right? So it's W1, right? Let's see applying the rule we just discussed how we compute that, right? So it's partial L over partial W 111, right? So how can we do that? Any thought? Yeah. So the path connecting which to which? More specific. So we need to see the target node, right? The target node on the edge corresponding to W111 is Z11, right? Yeah. We just look at, okay, starting from Z11, right? How many passes do we have to connect to the output neuron Y, right? 3, right? So let me just draw them out. So the remaining thing is quite mechanical, right? We just enumerate all the results, right? So let us look at the first pass, right? So it will be partial L or partial Y, right? Starting from here. Then we move to this node. The parent node is Y, and the parent node is partial Z02, right? Then we move to Z11, right? So parent node is Z02, then over partial Z11. And finally, don't forget partial Z11 over this weight, right? It's partial Z11 over partial W111, right? This is just one part of the result, right? So now we need to add the result of the second part, right? Maybe I should use this color, right? Second part, right? So, which is partial L or partial Y again, right? Now you intermediate node is Z12, right? So it's partial Y or partial Z12, then times partial Z12 over partial Z11, right? Times partial Z11 over partial W111. This is the second result, right? And then, please bear with me. We have to do a little bit tedious job to show the idea, right? The third pass, right? So, which is plus partial L or partial Y, and then this is node, right? This is second node, partial Y or partial Z22 times partial Z22 over partial Z11, then times partial Z11 over partial W111, right? So now we finish the result. Sorry, let me erase this duplicated plus here. So of course, we know that all the classes, they share the same term in the end, right? So why not we just comment it out, right? We just take it out so we can use a big parentheses. Okay. We got all the results. All the passes, right? We multiply the partial derivatives to Z11, and then add them together, then we get partial Z11 or partial W111, right? So now, who can tell me what can you observe by looking at the summation of the three products inside this parentheses to the result? Let me circle them, right? Does this result reflect some other meaning? What does this result mean? Yeah, exactly, right? So you can see that this summation, the summation of these three results is partial Y, partial Z02, and partial Z11, partial Y, partial Z12, partial Z11, partial Y, partial Z22, partial Z01, right? We add them together. This is essentially equals to what? According to the chain rule, This is a partial L over partial Z11, right? Isn't it? Right? This is our definition. So now we can see that we actually can reduce the computation of partial derivative with any edge weight to be a very simple form, right? Just calculate partial L over the partial of the target node, right? Which is partial Z11 here, then times partial Z11 over partial W11. Right? So now, suppose I want to compute another edge weight, right? Which also connects to Z11, right? So say the edge which connects X2 to Z11, right? The edge weight here will be denoted as 211, right? How do we compute partial L over partial W 211? Yeah, exactly, right? So you don't need to repeat this whole bunch of things, right? You just write down partial L over partial Z11 times partial Z11 over partial W211, right? That's it. What can this insight bring to us? Remember, if we just follow the previous rule, right? If we want to compute partial W111, partial W211, right? You have to repeat this bunch of things inside this, red block, right? It's really tedious and expensive. However, if you can efficiently compute partial derivative of the target node and catch them, right? You don't need to repeat this, right? You can directly load it and plug in. That's it. Right? The only difference is that you can every time you have to compute the partial target node over your specific weight. That's inevitable because these things are new, right? You cannot avoid them. So here comes the idea of the backpropagation. So every time from the output neuron to the input layer, that's why it's called backward direction. Because when we do the forward pass, we are propagating the input information to the output neuron to make prediction. We call it the forward direction, right? But when we do the gradient calculation, we start from the output neuron, then to the input layer. So it's called backward propagation. So every time we not only compute partial derivative with respect to the weights, but also compute partial derivative with respect to the neurons. And then we move to the one layer below, right? We compute the partial derivative of the neurons based upon the results of the partial derivatives of previous neurons. Then you don't need to backtrack to all the way top to the output neuron. And once you get partial derivatives with respect to neurons, you can just use them to calculate partial derivatives on the edge weights connects to these neurons. That's the high level idea. But before I proceed to the detailed example, any questions so far? Or any concerns so far? Is everyone good? Okay, so now I want to use this example again to show how are we gonna use backpropagation to efficiently compute the partial derivative of the loss with respect to every edge weight. Okay. Yeah, so let me draw the figure again. So this is layer 0, this is layer 1, this is layer 2, that's layer 3. So finally, we got the alpha neuron. Okay, so this is x0, x1, and x2. So this is z01, z02. Oh, sorry. Z11 and z21. Z02, Z1, 2, Z2, 2, and finally we got 1, right? So, of course, the Y is fitted into a loss. It can be noted by a virtual node. Okay. So now, let us perform backpropagation. So let's, as I said, we're gonna do it layer by layer. We start with the alpha layer. So in the very first step, we're gonna start with the alpha layer. So step 1. So the objective in the alpha layer is that, okay, we're gonna first compute the partial derivative of the loss with respect to all the neurons in the alpha layer. Right? Of course, in alpha layer, we only have one neuron, so it's only has a partial L or partial Y. And then we're going to compute the partial derivative of the loss with respect to all the edge weights pointing to the neurons in the alpha layer. So here we have 3 edge weights, right? So which is here, which is W 0, 1, 3, W 1, 1, 3, W 2, 1, 3. Right? So remember, we index the output neuron by 1, right? And the target layer is 3. That's why we denote the edge weight here by W1, 0, 1, 3, W1, 3, W2, 3. So we're going to compute the partial derivative loss with respect to all the edge weights pointing to the neurons in the output neuron, in the output layer, which is partial L over partial W 0, 1, 3, partial L over partial W 1, 1, 3, partial L over partial W 2, 1, 3. Okay, this is our task in the first step. But the task in every step is actually the same. We move to the next layer. We compute the partial derivatives with respect to all the neurons in that layer, and then partial derivatives with respect to all the edge weights pointing to the neurons in that layer. It's all the same, right? But we're gonna leverage the results we calculated from the previous step. So okay, so let us look at how we finish step 1, right? So first, partial L over partial Y is Y minus the ground truth. That's easy, right? And then, how do we compute the partial L over partial W0, 1, 3? Any thought? Yeah, exactly right. Just as we just mentioned, right? You first read out partial L over partial of its target node, and then just calculate partial target node over the weight, right? So it's a partial L over partial Y times partial Y over partial W 0, 1, 3, right? And similarly, partial L over partial W 0, sorry, 1, 1, 3 is partial L over partial Y, because remember the target node is always there, alpha node, right? Alpha neuron. And then alpha neuron over the partial weight, right? 113, right? And partial L over partial W 213 equals to partial L over partial Y, then times partial Y over partial W 213. And this is pretty easy because Y is a linear combination, right? So we know that it's W 0, 1, 3 times Z02 plus W 113 times Z12 plus W 213 times Z22, right? So if you want to compute the partial Y over each of those weights, it's pretty straightforward. Okay, so now we finished step 1, right? So we're gonna move one layer below, right? We move to layer 2. Right? So in layer 2, we're going to use the results of step 1 to compute the partial derivative of the loss with respect to all the nodes in layer 2. So now in layer 2, we have 3 nodes, right? That means we have to compute the partial derivative with respect to 3 neurons, right? So it includes partial Z02, partial L over partial Z12, partial L over partial Z22, right? Those are about neurons, right? But in addition, we're gonna compute the partial derivative of all the edge weights pointing to those 3 neurons, right? There are many. There are quite a few, right? So I'm not gonna enumerate them. I'll just succinctly represent them like partial L over partial Wij2, because the target layer 2, right? So those edge weights, right? You can see those edge weights, their edges pointing to any of the neurons in the layer 2, right? So again, let's see how do we compute partial L over partial Z02, right? How to compute that? Yeah. How to use previous result? Give me the formula. Z02. Yeah, exactly right. So remember, we mentioned when we apply the chain rule, right? We look at, okay, from Z02 to Y, there's only one path, right? So if you want to compute partial L over partial Z02, you just look at this path, right? So then you multiply the result along the path. This is partial L over, sorry, it's not, you don't need to look at the path. You just look at how many connections from Z02 to Y, right? You only have one, right? So you got partial L over partial Y, then times partial Y over partial Z02. That's it, right? And similarly, how do you compute partial L over partial Z12? Any suggestion? Yeah, right? Partial L over partial y times partial y over partial z 1, 2, right? So look, the results are reused, right? Partial L over partial y, adjust the result we computed in the first step, right? And similarly, we compute partial L over partial z22 by partial L over partial y times partial y over partial z22, right? So you can see how those results are reused, right? We reuse partial L over partial y, right? The partial derivative with respect to the neurons in previous in the one layer above, right? They have already been computed and cached. Any questions so far? It's pretty straightforward, right? So once we get the partial derivatives of all the neurons in layer 2, right? Suppose I want to compute any edge weight pointing to those neurons, right? How do we compute? Right? For example, suppose we want to compute the edge weight here, right? Which is denoted by W222, right? So how do we compute the partial L over partial W222? Any thought? Yeah, right? Look at target node, right? The target node, the way the edge pointing to this Z22, right? So you use the result about Z22, right? So partial L or partial Z22, then times partial Z22 over partial W222, right? So similar rule is applied to any other edge weight pointing to the 3 neurons, right? So now we finished step 2. Right? So we're gonna move one layer below. Right? Again, in step 3, again, our goal is to compute the partial derivatives of the loss with respect to all the neurons in layer 1. And of course, all the edge weights pointing to the neurons in layer 1, right? But right now, for this layer, you gotta be careful because let us use one example to illustrate this point. Right? Suppose we want to compute partial L over partial Z11. How to compute that? Yes, right. This is very important. That's why we always emphasize looking at the structure, right? So you can see that Z11 pointing to or connecting to all the neurons in the next layer, right? That means all the neurons in layer 2 are dependent on Z11. So if you want to compute them, you need to leverage the results, right? So again, applying the chain rule is equal to partial L over partial Z02 times partial Z02 over partial Z11, right? This is just one result, right? Well, here, right? And this one, partial L over partial Z12 times partial Z12 over partial Z11, and then plus partial L over partial Z22 times partial Z22 over partial Z11, right? But don't forget, because you need to look at how the neurons in the next layer are dependent on your current neuron, right? And similarly, when you compute a partial L over partial Z 0 to 1. So can anyone help me finish the formula? Yes, exactly right. And yeah, I'm gonna just copy, paste, and then made a change accordingly. Okay. So you're gonna change the partial derivative here. Right? So it's a partial Z02 or partial Z01, right? Because all the neurons in the next layer, in layer 2, are dependent on Z01. So you have to leverage all of their results, right? So Z01, 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 right? Similarly, you can compute the partial derivative of the loss with respect to Z21, right? Again, suppose you have obtained all the partial derivatives with respect to the neurons in layer 1. How do we compute the partial derivatives with respect to the attributes? Right? I'm going to use another example to emphasize. Right? So suppose I want to compute the attribute here, right? So it is denoted by W0, 2, 1, right? So how do we compute partial L or partial W0, 2, 1? So this is WZ21, right? Given the results we have already obtained. How to do that? Yes, exactly right. Just look at the target node. This edge pointing to Z21, so it's partial L over partial W. Sorry, it's not W. Partial Z to 1, then times partial Z to 1 over partial W to 0 to 1, right? That's it. So you can see this procedure, right? Every time, no matter in which depths we have we have been, right? We never need to backtrack to the top layer, the output layer, like long way, right? We just leverage the results from the previous step. That is the results from the one layer above. It's enough for us to compute. And once we get the partial derivatives with respect to neurons, the computation of the connected weights is much easier, right? You just look at the target nodes and multiply the partial derivative of the target node with respect to weight. That's it. In this way, so this is called back propagation. In this way, it can like maximally reduce the computation because it avoids all possible duplicated computation. All new computation is something you have to compute. You cannot avoid it. But other than that, everything, other than that, you don't waste any cost or time to recompute anything. So any questions so far? And hopefully this procedure will give you a detailed example to show how the backpropagation works. Okay? So, and I will highly recommend you to follow the manual example here. right? Do it by yourself. Actually, our homework 5, actually our last homework, before you implement propagation, I have given you assignment, a manual assignment to do this manually. That will definitely strengthen your impression how the propagation works. Okay, I'm gonna just give a general description of this propagation procedure, but I believe the whole details are already there, right? So the propagation essentially is to repeatedly apply the chain rule for partial derivatives. So first, we're gonna perform forward pass from the input to output to compute loss, right? Of course, right? Then from loss, we proceed backwards to compute the partial derivatives over the nodes and the weights using the chain rule. Remember, we over both the nodes and weights. Right? We first compute nodes based on the partial derivatives of the nodes one layer above. And that means we don't necessarily need to go backtrack to the output neuron. We just use leverage the results of the nodes in the layer above. And then we use the chain rule to compute the partial derivative with respect to weights. Then we catch those partial derivatives and proceed to one layer bottom. Right? And you do this again and again until we reach the input layer, until you finish completion. Right? And because this procedure is pretty mechanistic, so this procedure has already been implemented in the modern neural network libraries, including PyTorch, including TensorFlow, including I forgot other libraries. Yeah, the word coming into my mouth, and just I lost it. But anyway, there are many libraries used kind of similar ideas to implement the backpropagation, but of course they're implemented in a much more numerical, stable way, much more efficient way. Like they combine all the matrix computation inversion operations together. But here, going back to our stochastic gradient descent framework to train a neural network, right? At the beginning, we have illustrated that we just follow the standard framework we discussed before. We can fulfill our neural network training, right? So we go through the data many epochs, and inside each epoch, we shuffle the training examples. And for each training example, right, we treat this example as the data set, and then we calculate the loss, right? The loss on this particular example. Then we calculate the gradient of the loss as our stochastic gradient, right? And then update our model parameters. The model parameters here refer to all the attributes in a neural network, right? But as we mentioned, the bottleneck is how to efficiently compute this gradient, the gradient of the loss on this random sample example, right? And here we can replace this gray box by the backpropagation procedure. Right? That's what you're going to do in your homework. Okay, let's stop here.